Welcome to English for Professional Mechanical Engineers. My name is Jun Tu. I'm happy to have this chance to speak to you today about Computer-Aided Engineer, CAE. In this lesson, we are going to introduce the fifth section of CAE, Vibration Analysis. Vibration is a mechanical phenomenon whereby oscillations occur at about an equilibrium point. The oscillation may be periodic, such as the motion of pendulum, or random, such as the movement of a tire on a gravel road. Vibration can be desirable. For example, the motion of tuning fork, the reed in a woodwind instrument or harmonica, a mobile phone, or the cone of loudspeaker. In many cases, however, vibration is undesirable, wasting energy and creating unwanted sound. For example, the vibrational motion of an engines, electric motors, or any mechanical device in operation are typical unwanted. Such vibrations could be caused by imbalances in rotating parts, uneven friction, or the machining of gear teeth. Careful design usually minimizes unwanted vibrations. The studies of sound and vibrations are closely related. Sounds or pressure waves are generated by vibrating in structure, for example, vocal cords. These pressure waves can also induce vibration of structures, for example, eardrum. Hence, attempts to reduce noise are often related to the issue of vibration. Free vibration occurs when a mechanical system is set in motion with an initial input and allowed to vibrate freely. Examples of this type of vibration are putting a chair back on a swing and let go, or hitting a tuning fork and letting it ring. The mechanical system vibrates at one or more of its natural frequencies and damped down to motionlessness. Forced vibration is when a time-varying disturbance, such as load, displacement, or velocity, is applied to a mechanical system. The disturbance can be periodic and a steady-state input, a transient input, or a random input. The periodic input can be harmonic or a non-harmonic disturbance. Examples of these types of vibration include a washing machine shaking due to an imbalance, transportation vibration caused by an engineer or uneven loads, or the vibration of a building during an earthquake. For a linear system, the frequency of the steady vibration response resulting from the application of a periodic harmonic input is equal to the frequency of the applied force or motion, with the response magnitude being dependent on the actual mechanical system. When the energy of vibrating system is gradually dissipated by friction and other resistance, the vibrations are said to be damped. The vibration gradually reduced or change its frequency or intensity, and the system rests in its equilibrium position. Vibration analysis, VA, applied in an industrial and maintenance environment aim to reduce maintenance cost and the equipment downtime by detecting equipment fault. VA is a key component of the conditional monitoring program, and is often referred to as predictive maintenance, PDM. Most commonly, VA is used to detect fault in rotating equipment such as fans, motor, pumps, and gearboxes, and so on. Such unbalanced misalignment, rolling element bearing fault, and resonance conditions. We can use the unit of displacement, velocity, and acceleration displayed as a time waveform, TWF. But most commonly, the spectrum is used, derived from a fast Fourier transform of the TWF. The vibration spectrum provides important frequency information that can pinpoint the fault component. The fundamental of vibration analysis can be understood by the simple mass spring damper model. Indeed, even a complex structure such as an automobile body can be modeled as a summation of a simple mass spring damper models. The mass spring damper models is an example of a simple harmonic oscillator. The mathematics used to describe its behaviors is identical to other simple harmonic oscillator, such as RLC circuit. Model analysis is the study of the dynamic property of systems in frequency domain. A typical example would be testing structures under vibrational excitation. In other words, model analysis is the field of measuring and calculating and analyzing dynamic response of the structure and the fluid or other systems during excitation. Example would include measure the vibration of a body when it's attached to an electromagnetic circuit. Analysis of unforced vibration response of vehicle suspension or the noise pattern in a room when excited by a loudspeaker. Modern-day experimental model analysis systems are composed of 1. Sensors, such as transducer, typically accelerometer, load cell, or non-contact via laser via barometer, or stereophotogrammic cameras. 2. Data acquisition system, and an analog to digital converter front end to digitize analog instrument signal. And 3. Host personal computer to view the data and analyze it. The results can also be used correlated with finite element analysis normal model solutions. When there are many degrees of freedom, one method of visualization of the mode shape is by animate them using structural analysis software. An example of animated mode shape is shown in the figure below for a cantilever I-beam, as demonstrated using model analysis on ANSYS. In this case, the finite element method was used to generate an approximation of the mass and the stiffness matrices by measuring the object of interest in order to solve a discrete eigenvalue problems. Note that in this case, the finite element method provides an approximation of meshed surface, for which there is this infinite number of vibration modes and frequencies. Therefore, the relatively simple model that has over 100 degrees of freedom and hence as many natural frequencies and mode shapes provides a good approximation for the first natural frequencies and modes. Generally, only the first few modes are important for practical applications. In this table, the first and the second horizontal bending, torsion in middle, and the vertical bending in right vibration mode of an I-beam are visualized. There are also exist other kind of vibrational mode in which the beam gets compressed, strengthened out of in the height, width, and the length duration respectively. Similarly, another example of mode shape is shown in the figure for an inspective CCD camera frame using model analysis on POEM. The horizontal bending, torsional, and the vertical bending vibration mode of the CCD camera frame are visualized. Note that when performing a numerical approximation of a mathematical model, convergence of the parameters of interest must be ascertained. Does all the results make sense? Finally, we have some questions for you. Question 1. A mechanical system is set in motion with an initial input and allowed to vibrate freely. The type of vibration of this system is usually called as A. Free vibration, B. Forced vibration, C. Damped vibration, D. Steady state vibration. Yes, the answer is A. Free vibration. Did you get it? Question 2. Model analysis is the study of dynamic property of system in the frequency domain. Except the natural frequency, which physical property of the structure can also be determined by model analysis. A. Displacement, B. Velocity, C. Acceleration, D. Mode shape. The answer is D. Mode shape. So this is the end of this session, vibration analysis. I will see you again in next video. Goodbye.